Alright, so this video is going to focus on the first section of chemical kinetics, factors that influence how fast reactions can occur. And kinetics is just a fancy word to examine the rate at which reactions proceed. Some reactions occur more quickly, such as a gas combusting in the presence of oxygen, and some take a lot longer to occur, such as iron rusting. And so there are several factors that can affect how fast a reaction will take place, and we're going to examine some of those right now. The speed at which a reaction occurs is known as its reaction rate, and basically it's looking at how quickly the reactants are consumed or how quickly the products are formed over a period of time. And since rates are usually measured by a change in some sort of amount, we're going to look at change in concentration over that period of time. When reactants are consumed, their reaction rates are going to result in a net negative difference, while when products are formed, they are being produced, so their rates would definitely be positive. When you're comparing rates of a reactant to a product, or a product to another product, or even a reactant to a reactant, we can determine what those rates are based on the stoichiometric ratios that are present in our balanced equation. So here we're looking at the reaction in which ammonia is made between nitrogen and hydrogen, and we see that it makes 2 ammonia molecules. We want to know what the production rate is for ammonia and the consumption rate for hydrogen if nitrogen is consumed at a rate of 3 molar per minute. So if we know nitrogen is being used up 3 molar for every minute that we use it, we can look at the relationship between nitrogen and ammonia in the balanced equation, that there's 1 nitrogen molecule for every 2 ammonia molecules. And so if we start with the 3 molar per minute of nitrogen consumed, and we allow nitrogen to get canceled out and ammonia to be formed, we see that that's a 1:2 ratio. So the rate ammonia is produced at would be roughly twice the rate at which nitrogen is being consumed. It would be at 6 molar per minute. Now if we look at hydrogen, we see that if we go again with nitrogen being consumed at 3 molar per minute, we see the relationship between nitrogen and hydrogen in the balanced equation is a 1:3 ratio. So if we start with our nitrogen at 3 molar per minute, and we see that 1 nitrogen molecule is used along with 3 hydrogen molecules, the nitrogens cancel out, and we would see that the ratio would be increased by a factor of 3, proportionally to the stoichiometric ratio in our balanced equation, that 9 molar per minute of hydrogen would be consumed. Some reactions take longer to occur, in part because of the activation energy that's needed to get the slowest step in the reaction to reach that transition state in which the reactants can transform into products. We talked a little bit about collision theory in your first chemistry class, that not every collision results in a reaction because sometimes they just don't have enough juice. I know, like when I start my lawnmower up at the beginning of the spring, first couple of pulls does not usually get it going, but usually after it's got a little bit of energy in there, you can get it to go over and the gasoline will start to be consumed. Or sometimes you might have molecules not hitting each other on the right side, and they would not be as willing to form products. And so we're going to see that some reactions can require multiple steps before there's enough energy, sufficient energy for the reactants to transform to become products. And the collision model is just one way to describe how those steps take place. So there's 4 factors I'm going to talk about how they can influence the rate of a reaction. First one we're going to look at is concentration, that as the concentration of a reactant increases, as there are more molecules present. If you look at the pictures below, you can see beaker 2 has more molecules of substance A than did beaker 1. It has roughly twice the amount. That's going to increase the likelihood that substance A and substance B are going to interact with each other, collide more often, and that should help to speed up your reaction. The second one we're going to look at is pressure. This would only be effective for a gas because our solid and liquid states are incompressible. The pressure of a gas, if we push down on the container's top, we would be reducing the volume, and that would push the molecules closer to one another. So when you are at a higher pressure, a reduced volume, you are increasing the likelihood that the particles are going to collide together more often than you would if you were at a lower pressure and a larger volume. And so reducing the volume by increasing the pressure will allow your particles to collide more frequently, speeding up your reactions rate. Surface area is what particle size is talking about. If you look at substance A, you'll see that it's just in a nice, neat rectangle. There's 12 red circles, and the two on the inside aren't really close to all the blue circles on the outside. Whereas when you have it in a more powdered form, they're not really glued together, and so those blue particles are going to be much more likely to interact with the powdered form quickly than they would with the chunk form. You can only react with what's available for interaction, and so when you kind of have it clumped together, I know when I bake, I try to make sure if I'm using something that can clump that I break up those clumps beforehand, because I know it's going to take longer to prepare the mixture when it's kind of clumpy. So the more particles that are available for interactions, the more particles are available for collisions, and that's going to help to facilitate your reaction rate becoming faster. And then the last one we're going to talk about is temperature. When you have a greater temperature, you have more kinetic energy. If you have more motion energy, you're going to be moving around more quickly, and that's going to help you to reach that activation energy threshold so that the reactants can become products. Basically, if you have a 10 degrees Celsius increase in temperature, your rate should pretty much double. So to try to explain this diagram below, this would be at a low temperature, and this one would be at a high temperature. We see at the low temperature there's a much greater peak. There's a lot more particles at the peak of this curve, but they're at a much lower energy. While with the higher temperature, we see more of a plateau, and we don't have nearly the number of molecules at the peak that we did with the low temperature. But as we continue going and we reach that activation energy threshold, we see that this small area under the triangle at the low temperature is much less than this area underneath the high temperature curve. So we're going to have a lot more particles that are going to reach that activation energy component and therefore be able to become products at a much faster rate than they would at a lower temperature. The last thing, I'm sorry, I thought that we were done. One last one is a catalyst. Catalysts help to speed up your reaction, but they themselves are not changed in the actual reaction. They basically make it so that there's a shortcut, so that path isn't as steep, that the activation energy requirement isn't as large, and that helps to transform your reactants into products much more quickly. Enzymes are often referred to as catalysts, and they do this in the human body and a lot of biochemical reactions that if you pursue anything in the biological sciences, you'll get a chance to see. Hopefully you remember this graph a little bit. We're going to go through one example with this, I think next slide, how the reactants and the products both come with their own set of energy. That's the potential energy of the reactants and the potential energy of the products. That the difference between the products and reactants energy is your enthalpy of your reaction. They're calling it delta E, but it could also be delta H of the reaction. And then the activation energy is from where the reactants start up to the peak of the hill, whether it be catalyzed or whether it be uncatalyzed. This is an endothermic reaction because the products ended up with more energy than the reactants. If it had been exothermic, it would have ended lower because the products would have released energy as a result of the reaction proceeding. And we'll get a chance to see an exothermic one on this particular graph. I've told you the enthalpy of the reaction is negative 10 kilojoules per mole, and that the activation energy requirement was 50 kilojoules per mole. We're just going to kind of sketch out what this graph would look like. Because delta E is negative, this is an exothermic reaction. So if I was going to draw the curve, the products line would end lower than the reactants line. The difference between the products and the reactants line would be your delta E value. Okay, one below it. And then the activation energy is from where the reactants came to the graph, where they came with their potential energy, up to that activated complex, the peak of the hill, where the reactants can transform to become products. And I believe this is the end of your first section of notes.